Okay, why don't we go ahead and get started? Thank you all for joining. The session you are about to attend is called Improving Your Android App to Prevent Security Vulnerabilities. We welcome your questions and your comments. We appreciate if you would use the chat function on the bottom of your screen of your Zoom meeting to let us know what questions that you have. The presentation will run about 15-20 minutes, and then we'll field your questions, and we'll also try to answer them during the course of the presentation too. If for some reason there's a technical issue and you happen to get disconnected, or the meeting seems to end early, go ahead and give that link a try once again. We'll be opening it immediately back up. So far, we've had great luck and no issues today, but I thought I'd put that out there just in case. With that in mind, please allow me to turn it over to our Google panelists today, and I'll let them introduce themselves. Thank you.
Hello, everyone. My name is Kostya, and I'm leading various efforts related to memory safety across Android, Chrome, and Google server-side applications.
My name is Peter. I'm a software engineer at Google, and I'm working on Android support for some of the new ARM v9 extensions, specifically focusing on the memory tagging extension.
Hi, my name is Mitch. I'm a software engineer from the Dynamic Tools team. I work on both memory tagging and GWP-ASan, some of the things you'll be hearing about today.
Hi, I'm Evgenii. I'm working on the same team as the rest of us on MTE in Android, and also on some of the other tools that I'll be telling you about today. How about we start with the presentation? The title is Improving the Android App to Prevent Security Vulnerabilities. The main topic here, of course, is C++ memory safety. And memory corruption issues in C++ in native code are known as a leading cause of security vulnerabilities. This slide shows that significantly more than half of all security issues found by Project Zero and also CVEs in Android have memory corruption as the root cause. Memory corruption bugs are not only security vulnerabilities, they are also issues that are very hard to track down, debug, and fix. The reason is that a burst crash often happens far away from the original memory corruption, and crash report does not give you enough information to root cause the problem. There are tools that allow you to detect and fix such bugs, but they typically have high overhead and are difficult to use. And especially there is no good way to track down bugs that cannot be reproduced on the developer machine, which happens quite often with this type of bugs. So the memory tagging extension is expected to help a lot in this regard. It's an optional extension. It was introduced about 2 years ago by ARM. It is 64 bits only, and it introduces two types of tags. There are logical address tags, which reside in the pointer, in the most significant byte of the pointer. And there is an allocation tag, which is RAM metadata. It's 4 bits for every 16 bytes of memory. Allocation tags are stored separately. They're not directly accessible by the usual load and store instructions, but there are special instructions that can be used to maintain and read these tags. And the main idea of the extension is that most load and store instructions raise an exception if pointer tag is not the same as the memory tag. There are two modes of this extension. One is synchronous. which in this mode, the process dies with a segmentation fault immediately as soon as a tag mismatch happens, and an asynchronous mode, which is faster, but in that mode, the process dies slightly later, namely at the nearest context switch. And asynchronous mode doesn't provide a lot of information about what happens. It basically just a flag. There is something wrong happened in your program. So it's a security mitigation mode, first of all. This is an example of how this extension can be used to protect heap memory from corruption. On this slide, tags are color-coded. For example, red stands for 0xA tag. And as you can see, if a pointer is used for an out-of-bounds access, p index 32 in this case, the pointer tag will not match the memory allocation tag, and the process will crash. When memory is deallocated, memory tags are changed once again randomly, and an attempt to use a dangling pointer will also result in a crash and a crash report. We're working on implementing this in Android now, in AOSP. There are instructions. There is a link at the bottom of this slide. You can build it and run it on the ARM fixed virtual platform simulator. The implementation plan is like this. We expect to enable asynchronous mode heap tagging in all system apps and all the platform native daemons components by default. And user apps will not get it by default for stability reasons, but they can opt in. There is a manifest attribute which can enable heap tagging in an app, and it can also select between async and sync modes. We're also developing an API that can be used to enable sync modes and debugging features in the allocator at runtime. As for crash reporting, asynchronous mode, the fast one, doesn't give us almost anything. It's basically a mitigation mode. It prevents attackers from abusing memory corruption bugs, but it doesn't let you debug them. On the other hand, the synchronous mode can provide an exact stack trace of when the problem happened. And we have extra support in the memory allocator that allows us to record allocation and deallocation stack trace and associate them with a particular fault. As a result, we can provide enhanced crash reports that have allocation and deallocation stack traces that describe the allocation, for example, size and offset of the memory access. In the end, the reports look very similar to address sanitizer report, if you've seen those. The reports, these enhanced reports go to all the places where crash reports are usually found in Android, Logcat, Tombstones, Play Console, Android Vitals, and so on. This is an example of what we are able to produce. You can see that it's a segmentation fault with a specific code, MTESR, that can be used to recognize such problems. It has a cause line, which displays what we think happened, use of the free in this case, the offset and the allocation size, followed by the usual backtrace, and then followed by two more stack traces. This is where this memory was most recently allocated and where it was previously deallocated. We can provide the same protection for stack and global memory, but not immediately. The reason is that applying tagging to stack and globals requires code instrumentation. The compiler needs to insert new instructions in the code, and those instructions are ARMv9 only. They will not run on ARMv8, and as such, a binary with such instructions cannot be shipped in Play Store. It can be used for local debugging, and eventually we expect that a new application API in Android will be introduced that will have hardware MTE support as the requirement, and then applications will be able to target such devices with stack and global protection. This is just for information, a slide that shows how stack tagging works. We insert just a few new instructions. This IRG instruction inserts a tag into the stack pointer and copies into a register, and then STGP stores initializes the local variable and also changes the allocation tags for it to match the pointer. And then one more instruction at the end restores the allocation tags to what they were originally. So it's a known fact that all code has lots of memory bugs. Code that has not been well tested with memory tools has a lot of them, typically. And MTE, when enabled, will catch all of them with a pretty high probability. It's not deterministic because there is only a limited number of tags, but the probability of detecting any tag is very high, it's more than 90%. So simply going ahead and enabling MTE in your application is likely to make it crash a lot. So how not to get overwhelmed by this? We have tools that you can use right now to test your code for memory bugs. And the first of those tools we call GWP-ASan. It is something that's enabled in Android 11. It runs on user devices. It uses allocation sampling and page protection mechanism. Any allocation, some allocations, a small percentage of allocations are routed to a special allocator that locates them near a guard page. Therefore, an attempt to overflow the allocation or overread it will hit a page that's mapped with no access permissions at all and cause a usual segmentation fault. When memory is deallocated, it is replaced with another guard page, and then an attempt to use a dangling painter will again cause a crash. Of course, this is pretty slow. Page protection requires a system call. Therefore, we simply do it very, very rarely. First of all, each process gets this thing enabled with about 1% probability. And then in those processes that have it enabled, we only sample a very tiny fraction, about 1 out of 2,500 allocations randomly, and give them this treatment. And as a result, the overhead of this is in the noise. The chance to detect each occurrence of a bug is very low, but given a significant user base and time, even the most rare bugs are likely to be detected eventually. As I mentioned, it's on by default in Android 11. User applications can opt in. Crash reports are very similar to the MTE crash reports that I've shown earlier, and you can see them in your Play console or whatever other mechanism is used to deliver crash reports for the applications. This is something that you can use right now. Here we have a video recorded by Mitch that shows some of these details. The manifest attribute. And this is our test app. It can be found, it's shared in the internet. It has a bunch of buttons that can trigger different memory corruption errors just for testing. And one of the buttons does a loop with a memory corruption, with a bad memory access in each loop iteration. The loop is needed because GWP-ASan is sampled, and a single bad memory access is likely to not be detected. Now we are going to launch this application and watch a logcat for crash reports. So now Mitch is clicking a button that causes just one memory access, nothing really happens. And the button that does loop in read immediately crashes the application with a crash report in the logs. Let's scroll up a little bit. Yeah, so there it is. It has a cause line very similar to the MTE cause line, the backtrace with the frames in the application code in the native library of the application. It's long. And then two more stack traces, allocation and deallocation. We have one more tool. It's called GWP-ASan, Hardware Assisted Address Sanitizer. it's basically a software implementation of memory tagging. We have memory tags. They are 8 bits instead of 4, simply because we can. They are stored in a software allocated buffer. We call it shadow memory. And load and store instructions are checked using compile instrumentation. So during compilation, we insert this additional code. There is a call to this Khwasan check function. The function simply extracts a tag from the pointer, loads a tag from shadow, and compares them. And if they differ, it goes on to print a report. Report is again very similar to GWP-ASan and MT reports. Khwasan is available for both OS developers and app developers. There are instructions and public links. It's a little bit harder to use than GWP-ASan. It needs a special device image built with Khwasan. We have these binary images available for Pixel devices, and any other device can use an AOSP image built with this, following the OS developer's instruction. Since it uses compile instrumentation, it's significantly slower than, well, GWP-ASan or MT. It slows down your program by the factor of 2 approximately. It has a reasonably significant overhead in RAM and code size. So this is primarily a debugging tool, but in our experience, it is fast enough to use to test most interactive apps, and some of us are even carrying devices where everything is built with Khwasan for daily use. They're not as fast as regular devices. You're not going to ship this to the users, but they're good for testing things locally. And here is a high-level overview of all of these options. Just to remind you, MT is a future option that doesn't have any hardware available for it right now. GWP-ASan is something that can be used right now. In Android 11, it doesn't require recompilation. It has very, very small overhead in all dimensions. It has small bug detection chance per incident of a bug. But as I said before, if you run it long enough and if you ship it to a large number of users, you will get all your bugs eventually. Khwasan requires rebuilding, is significantly slower, but it is a lot more comprehensive, and it has a very high chance of detecting a bug. MT is a strict improvement on GWP-ASan. MT's second globals again require recompilation, and it is more of a thing for the future. There are some of the links here. I think all of them were shown in the slides before. We're ready to take your questions. Let's stay on this slide.
So Evgenii, I think, the number one question is probably, if I'm a developer, how do I prepare to use MTE in practical terms? Right,
so the first thing that I would recommend is trying GWP-ASan. GWP-ASan will catch most of the bugs that you will run into with MTE. Therefore, it's making sure that your applications work with GWP-ASan will help MTE a lot.
And that's available today, right? And that's available today for them to try.
Yes, that's available in Android 11, which was launched just like a month ago. But yes, it is available. And
great.
Yeah, go ahead.
So one of the other questions is, do we expect MTE bypasses due to its probabilistic nature?
Right, so MTE has 16 tags, therefore there is about 7 or 6% chance to not detect a bug and to let a potential exploit go through. It is randomized, meaning that an attacker is unlikely to be able to pick just the right tag for this, and it also means that they're likely to be at least a few attempts where the application will crash instead of getting exploited, so that can warn the users, and this also will likely show on any crash monitoring. In synchronous mode, such failed attempts will also provide a lot of extra information that is likely that would likely be sufficient to understand what is going on, and it is likely to expose the actual exploit that is being used by the attacker, which is expected to make attacks a lot more expensive for them. Basically, cost of exploiting such device should be significantly higher. We expect to see a lot more attacks that will bypass this. A lot less attacks.
Can you give an example of how much tougher it becomes when these bugs have been eliminated? Some of the other paths that they would go instead that are more difficult.
Well, it's hard to predict the future. This is memory corruption is a very large percent of all security vulnerabilities. There will always remain logical kind of bugs which we don't corrupt memory, but instead you just use some logic bug in the application.
And then do you see any other applications of MT in the future outside of C code?
I can imagine some kind of use of this for maybe garbage collection algorithms. MT sounds like a great way of setting watch points. When you debug your native code, MT basically lets you set an unlimited number of watch points for free, while the usual debugging hardware limits you to 4, typically. We're thinking of ways to use it to detect more classes of memory bugs, in particular, an overflow within an allocation. For example, if you have a struct, an aggregate in C++, an overflow between 2 fields of this aggregate will not be caught with this approach, but maybe there is something we can do in the future to improve that. That's what.
Can you talk a little bit about some of the MT savings that you've seen as you've been trialing it and working with us on this?
Sorry, MT savings?
Some of the things that you found. So some of the security vulnerabilities that you were able to find using MT.
Well, so far we're working on, so far there's no MT hardware, so all we're able to do is run it on simulators, which are realistically too slow to detect anything that's not detectable with the existing tools. GWP-ASan has produced a significant number in the hundreds of the same type of bugs in the Android platform. Quite a lot of them are security significant.
And then how about some details on what you expect the memory footprint to look like?
So MT requires 3% of memory to be reserved for tags. This is something that must be done at the boot time. So if you're considering enabling this in your application, that's not something that you will care about. That's a decision that the device manufacturer makes. Then there is a slight increase due to memory alignment because tags have 16-byte granularity. All memory allocations needs to be 16-byte aligned. We measure that it's significantly less than 1% on average. Synchronous mode needs some extra memory to store the allocation and deallocation stack traces. I think in the current implementation, it's about 4, maybe 4.5 megabytes per process. Synchronous mode is the mode that you typically use for debugging when you suspect that there are either active exploitation of your application or some common bugs. Synchronous mode has much lower overhead, and it should be the default mode when your goal is to just prevent random exploitations.
Yeah, so I think that's one of the things that we probably should clarify. I think we said that the upcoming mitigations based on MTE would crash a process at any time in memory. I think we should probably clarify for developers that in the beginning, these implementations will probably have an on and off switch type of thing.
Yes, in the beginning, by default, it will not be enabled in your application. So you can enable it with a manifest attribute, and if it ends up crashing your application too much, you can disable it and then, for example, use some of the other tools or use local debugging with MTE to find and fix all of those bugs.
Yeah, I think that's very nice functionality. That that you're able to change it in the manifest and decide if you want to use it or not.
Yeah.
So I wanted to remind everybody in the audience that if you have questions, please, use the chat to ask them. And then also wanted to invite the other members from Google to do, if there's anything you wanted to add to the discussion, now would be a great time. Okay, guys. I want to thank all of you for joining, especially the guys from Google. We appreciate the presentation. Evgenii, I think you had a slide on where to get more information.
Yes, this one?
Yeah, let's talk through that real quick.
Yeah, so there are some links here. For ASan, we have instructions for all OS developers and for application developers on the usual Android documentation sites, sourceandroid.com and developerandroid.com. The same goes for GWP-ASan. There is a link to the application that was used in the demonstration in the video. And for MTE, in case someone wants to try it on the simulator is slow. It slows down the code about 100x times slower. But there is a way to build AOSP Android and run it there and see taken in action.
All right, thanks Evgenii. Again, we really appreciate everybody's participation, and see you at the next session.
Thank you for coming.
Thanks, everybody.